Hey everybody, welcome back to another round of astronomy. And yeah, let's get going. Let's start off with the review question. So here I have plotted the position versus time graph. So position in the vertical axis, time in the horizontal. Now there's three carts plotted here, and let us assume that each cart is given the same push. Okay? Which cart is more massive? Yeah, you got it? Good, 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 good. Yeah, so the more massive cart, when given the same push, will accelerate less. And because it's accelerated less when it's initially pushed, that means as it's coasting along, it will have a lower speed. And so we see that cart C travels the least amount of distance. That would correspond to the lowest speed. That would correspond to the smallest acceleration, and therefore it must be the most massive. Okay? Yeah, good, good. Okay. Second question for you. Okay. Forces blank to the direction of motion change the objects blank. Go ahead, fill in the blanks. Yeah, you got it? Yeah, good, 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 good. And here there's two correct answers, right? I've left it so that you have two possible options. Option number one is that an object is moving, say to my left, probably your right, and you push in the same direction that it's moving. Okay? What happens? Yeah, the object speeds up. You could say forces parallel to motion speed up. Okay, so we'll say changes the object's speed. Okay, well, that's one possibility. The other possibility we discussed is that forces perpendicular to the motion change the object's, the direction. Okay. So we have two possibilities. Of course, you could have a combination of the two. The force is parallel, it isn't truly parallel, but not truly perpendicular. It's a combination of the two. Okay? And that means that you'll have a combination of the results. The object's speed will change and the direction will change. Okay? Okay, good. So to introduce today, not only did Newton give us the patterns that help us communicate the interaction between objects, okay? Newton's three laws. Okay? He also went through and very much studied how objects interact gravitationally. Okay? And he was able to actually tease out an equation that gives us the gravitational force between two objects. So that's what I'm going to display for you now. Okay? So let me walk you through this. On the left side, we have the force, and that's the gravitational force. Okay? Okay. Now on the right side, we see a couple of different terms. The first thing that I'll point out to you is that gravity is an inverse squared law. Gravity is not inversely proportional to distance. Gravity is inversely proportional to the distance squared. The reason I'm emphasizing this so much is because the problem I see all the time in my exams is that I'll say you double the distance and people will tell me the force of gravity goes down by half. Okay? Oh, nay, nay. No, that's not how it goes. If you double the distance, it will go down by a quarter. Okay? That's the factor decrease. Okay? So it's an inverse square law. I will also highlight that it is the distance between the centers of objects 1 and 2. So whatever two objects you use for the masses, R represents the distance between the center of those two masses. The second one, as I've highlighted, it depends on the product of the masses. If you have mass, then you are exerting a gravitational influence on all other objects that have mass. Okay? You don't feel it right now. Like right now, you are exerting a gravitational influence on the computer and, you know, your computer mouse and your keyboard and yada, yada, yada. Okay? The reason you don't feel that gravitational interaction, you're not feeling yourself being pulled across the room by your bookcase, is this third idea. Okay? And it's big G. Big G is a constant. It's called the gravitational constant, and it was first experimentally determined by, I believe, I think it was Danish physicist named Cavendish. Maybe it was English. I can't remember for sure. Okay? Cavendish found G, the value of big G, and it turns out it's wicked small, really small, like 10 to the negative 11th. Okay, that's 100 billionth. Right? And he found some you know, constant that goes out in front. Okay. So if we want to find the gravitational force between two objects, okay, say Greg and the Earth, we substitute in the gravitational constant that I've given you down here. We substitute in the mass of Greg and the mass of the Earth. And then we substitute in the center to center distance. Okay? The distance between the center of Greg, probably his belly button, and the Earth, the radius of the Earth. Well, the radius of the Earth is 64 million kilometers, or excuse me, not 64, 6.4 million meters. And Greg is, we'll say, 1 meter above the surface. Okay? So technically, we'd have to put 6400001 squared. Okay? In the most strictest sense. Of course, if you did 6.4 million, that extra, you drop that 1 meter, nobody's even going to notice. Okay. So here's a question. A 15 kilogram mass is resting on the surface of the Earth. What is the gravitational force acting on this mass due to the Earth? So go ahead, take a minute, have at it. You got it? Yeah, good. Okay, so let's go ahead and walk through. And this time I got everything typed up for you, okay? So let's go ahead. We have our gravitational force, our equation for the gravitational force. And I'll highlight one of the masses we're using is the Earth. Okay? And the second one is the mass of the 15 kilos. So I'll subscript that 15 kilos for us just to remind ourselves what we're doing. Okay? Now, because I'm resting, presumably the 15 kilogram mass is resting on the surface of the Earth. The center of that 15 kilogram mass is maybe 10 centimeters above the surface of the Earth. Okay? So in that sense, in that instance, I'll just use the radius of the Earth. I'll say that extra 15 centimeters, you know, whatever. Okay? So now we're in a position, let's go ahead and substitute in some values. Okay? So we have the gravitational constant, 6.67 times 10 to the negative 11th. Notice these units are newtons times meters squared over seconds squared. Okay? And the reason I mention that is that means we need to have, seconds squared, kilograms squared. That means that we need the mass of the Earth, the mass of our object, to be in kilograms, and we need our distances to be in meters. Okay. So we will go ahead. We substitute in the 6.67. We've got the mass of the Earth, which I gave you on the previous page. We've got our 15 kilogram mass and the radius of the Earth. Now, the other thing I should point out to you, okay, because we have a squared in the denominator, don't forget that you need to square everything in the parentheses, okay? Not just the number. Okay? So one of the common mistakes that I'll see is that people will write 6.4 squared times 10 to the 6th. Say, oh, nay, that's not, you have to square everything in the parentheses. Okay? In other words, you need to square the 6.4, but you also need to square the 10 to the 6th. Okay? Be careful about that. Let's pull out the powers of 10. So you notice I've taken the 10 to the 11th, I've taken the 10 to the 24th, I've taken the 10 to the 6th squared, and I've written those all off to the side. Okay? The advantage to the scientific notation is if we consider just that right term for a second, we can do that in our head. 10 to the negative 11th times 10 to the 24th, well, I need to add the exponents, so I get 10 to the 13th. Then I divide by 10 to the 12th. That means I subtract the exponents. And so this whole rigmarole right here is just equal to 10. Right, that's yeah. Okay, well, let's consider this left term for a second. Right? And here we'll ballpark. Again, I'm just trying to get some idea about very rough numbers in my head. I'll round this down to 6. So I have 6 times 6 divided by 6 squared. Yeah, so ballparkish, 6 times 6 divided by 6 squared. So ballparkish, this term should give us something like 15. Again, we're really ballparking it, okay, but it's a good estimation. So at the end of the day, we should get that the gravitational force acting on my 15 kilogram mass should be on the order of 150. And I've put in here newtons. That is the unit of force named after Isaac Newton. So these are called newtons. Newtons. Okay. Now, if you want to get an idea, okay, so there we go. We're done. We've taken care of the problem. To give you an idea about the gravitational force, or maybe give you a sense of a Newton, take a 1 liter bottle, fill it with water, and hold it there. That's about 10 newtons of force. Okay? Just to give you a conceptual idea. Gallon of milk is about 40 newtons. Or a 2 liter bottle, 20 newtons. Okay, so just walk around, kind of get a sense for it, but it's not very much. Okay? So that's really all I have for Newton's law of gravity in terms of quantitative. The last thing I would like to spend a little bit of time on is trying to explain Kepler's laws using our ideas of forces and accelerations. Remember, I said Kepler mentioned the pattern, but had no idea why the pattern was being followed. Newton came in with his idea about accelerations and forces, and in that conceptual model is able to give us an idea about why Kepler's laws are being followed. In addition, he introduces this idea of gravity, right? The idea that two objects can exert a force on each other even when they're not physically touching. Now we have an idea, we have a way of explaining how planets orbit the sun without having to be pasted on a physical sphere. Okay, you ready for it? Yeah, let's go. Question for you. You have 3 hockey pucks as viewed from above as they slide across the ice. Okay? You wish each to follow its respective path, so I've given you A, B, and C. And therefore, you need to hit each hockey puck with your hammer. Okay? First off, which path will require the most strikes? Yeah, you got it? Yeah, good. Corollary question, how do we change the direction that an object is going? Yeah, we have to hit it perpendicularly. Good. So the question really is, which object changes directions the most often? You say, okay, I got that. That's C. Okay, object C changes the most often. Okay. Oh, I should ask another corollary question. Right? Object C changes direction the most often. Which object looks the closest to a circle? Yeah, okay, object C. Yeah. Okay, good. Next question for you. Okay, so I hit the puck perpendicular to its motion in order to change its direction. Okay? Towards what location do all of those hammer strikes or strikes point? Yeah, you got it? And be specific. See if you can describe it in a specific location. Yeah, you notice? Yeah, so strike one is going that way. I hit it again, I hit it again, hit it again, hit it again, hit it again. You notice that all of those perpendicular strikes, as the object goes about its path, all of those perpendicular strikes are roughly towards the center of the circle. Right? Okay. Yeah. So let's ask ourselves, how do we get an object to move in a circle? What we do is we constantly apply a force that is perpendicular to the motion of the object. Well, how does that jive? Oh, gravity is attractive. So let me set up a scenario like this. If I set up a scenario where I have the sun, I have the earth, and let's go ahead and say that the earth is moving, we'll say to the left. Okay. What direction is the gravitational force on the earth due to the sun? Yeah, towards the sun, right? Gravity is attractive. So the earth is feeling a gravitational force towards the sun. You notice that that force is perpendicular to the direction that the earth is moving. And what will happen, it will be consistently perpendicular. The sun will constantly be exerting this gravitational force as the planet moves around. That force will be perpendicular to the motion of the planet, and so the planet goes in a circle. Okay. Hey, that's essentially Kepler's first law. Right? Yeah. Of course. Okay, well, it's slightly off. Okay, we need just a little bit more. So here we go. A comet orbits the sun in an elliptical orbit. Of course, I could have made this a planet. We'll just make it a comet. Okay? What is the approximate direction of the force acting on the comet? Yeah, you got it, right? We say, hey, gravity is still attractive. The force must be directed towards the sun. Okay? Yeah, I agree. Okay. Next question. If that is the direction, if we have the direction of motion, what I've been calling V, and we have the force, question, does the comet speed up or slow down? Yeah, good, it speeds up. You see that there is a bit of the, you could think of it as tugging in the parallel direction. Yeah. Well, does the comet change direction or does it keep heading in the same direction? Yeah, good. It also changes direction. There is a component, we would call it a component of the force, perpendicular. So both simultaneously, the comet is changing speed and changing direction. Okay? And so the fact that that force, the gravitational force, isn't truly perpendicular, it's off askew a little bit, means that rather than orbiting in a perfect circle, it orbits in an ellipse. Okay, now we definitely have Kepler's first law, excuse me. Let me ask another question here. Let's say we move the comet to the other side and we have it moving this way. You know that the gravitational force is this way. Does it speed up or slow down? Yeah, good, it slows down. Now you see that as it moves one way, it's got this gravitational force kind of pulling it backwards. Yeah. How about does it change direction? Yeah. Okay, good. So now we have an idea. We said, well, up here, the comet is moving this way. The force is this way. It speeds up. Okay? Down here, it speeds up, speeds up. Okay? Down here, as the comet moves away from the sun, the gravitational force slows the comet down. As it moves closer to the sun, it speeds up. As it moves further away, it slows down. Right? That is Kepler's second law. So now we have an idea that planets moving in elliptical orbits, because the gravitational force is not perpendicular to the direction that the planet is moving. We also have an idea that planets speed up as they approach the sun. They slow down as they're moving away, because the gravitational force is either tugging them in the same direction as they're moving or tugging them against the direction they're moving. Right? Like I said, Newton gives us a new layer in order to describe these interactions. Okay? So summary. Newton's laws plus the gravitational force help explain Kepler's laws. And byline, there is this underlying assumption that phenomena that I observe here on Earth is the same, is consistent elsewhere in the universe. Okay? So it's very nice that it relates it to everyday experiences. Okay? Now, you say, what's next? Where's the next model? Okay? The next model doesn't arrive until 1915 by a famous scientist and physicist, Albert Einstein. Okay? It's called general relativity. Like I said, this is in 1915. And that is the most complete model of gravity that we have. Okay? That being said, we're over a century later, and we have not yet done an experiment that has given results conflicting with general relativity. Okay? In fact, you're probably familiar, there's been several recent experiments within the last 5 years that have been built, developed, and executed just to test general relativity. Okay? You say, why wasn't it done back in 1915? It's because it took over a century of technological developments in order to perform these experiments. Okay? So it's beyond the scope of this course, but we can still get a qualitative understanding of what's going on. So I'll say full stop. Okay, well, I think that's it for right now. I thank you for your attention and your patience as I get a little bit jazzed about it, okay? But we'll come back to this hopefully later on in the semester, okay? So keep up the good work. Thanks for your attention. I'll see you next time.